In the name of God, good morning, dear attendees, and thank you for joining this presentation. I am Mobina Zivandepur, a master's student in mechatronics engineering at KN2C University of Technology. Today, I will present our research titled Design of a Tube Model Predictive Controller for Pneumatic Muscle Actuators Servomechanism under parametric uncertainty. Our objective is to propose a robust control strategy that addresses the challenge associated with controlling pneumatic muscle actuators (PMAs), which are widely used in biomechatronics and robotics. My presentation today will proceed as follows: introduction and research context, then mathematical modeling of the PMA system, then PID controller design and implementation. After that, I will speak about purpose tube MPC architecture, and then we will speak about noise analysis and system performance. At the end of this presentation, we will compare results and conclusions. Each section has been structured to provide a comprehensive understanding of our research methodology and findings. Pneumatic muscle actuators are widely used in biomechatronics and robotics due to their lightweight design and ability to mimic human muscles. However, controlling PMAs present challenges because of their nonlinear behavior and sensitivity to uncertainties like external disturbance and noise. This research focuses on designing a Tube Model Predictive Controller (MPC) to address this challenge. By integrating a robust MPC framework, we ensure accurate trajectory tracking and system stability, outperforming traditional PID controllers. The purpose controller's real-time performance and ability to manage uncertainties make it a reliable choice for complex dynamic systems. In the following image, you can see PMA classifications. In our work, we model the dynamics of PMAs using a mass spring damper system based on Reynolds model. This state presentation accounts for uncertainties in key system parameters including nonlinear spring force Kp as a function of internal pressure, pressure-dependent damping coefficient Bp, and contractile force Fb, which serves as the primary actuation force. The system is modeled to capture the nonlinear behavior of PMAs, especially the variation in contraction and extension caused by internal pressure changes. The system state equations were formulated within constraints beyond to address parametric uncertainties, with displacement x1 and velocity x2 being the control inputs. This model forms the basis for designing the control strategy. Here in this slide, you can see the equations and the range of the uncertainty we used in our study. Firstly, a PID controller was designed and optimized to establish a reference for comparison. The final tuning parameters, which are determined through trial and error, are here and you can see in this table. These values were optimized to ensure that performance criteria, such as settling time, overshoot, and steady-state error, are within acceptable limits. However, despite its simplicity, the PID controller exhibits limitations when dealing with nonlinearities and uncertainties in the PMA system. As you can see in the following plots, the output follows the input, but there are some distortions in the peaks of the plot. The purposed Tube MPC is designed to overcome the inherent limitations of PID controller, particularly in systems characterized by nonlinearities and parametric uncertainties. Two key parameters were adjusted during the design process. Prediction horizon was 20 and control horizon was 15. The sample time that we used was 0.01 seconds. Additionally, the following tuning parameters were optimized, as you can see here. The Tube MPC was designed to improve system stability and trajectory tracking, even in the presence of significant uncertainties. As you can see in the following plot, the output follows the input precisely, and it means the Tube MPC performance is better than the PID controller performance in our system. An essential part of the analysis involved evaluating the controller's robustness against noise. The left plot in this slide shows the system's response to a step input in the presence of Gaussian noise, with a variance of 0.001. We used a low-pass filter to mitigate the effect of noise and analyze the controller's performance in this condition. In the right plot, we demonstrate the behavior of the Tube MPC controller under noise after using a low-pass filter. The output follows the reference signal, but the system response time is longer. It doesn't mean that the control performance is not good in noisy conditions. In this slide, you can see the outputs of Tube MPC and PID controllers under noise with a low-pass filter. The results demonstrate that the Tube MPC provides superior noise rejection compared to the PID controller while maintaining precise trajectory tracking. This resilience against noise makes the Tube MPC particularly advantageous in real-world applications where disturbances are common. Our simulation results show that the Tube MPC outperforms the conventional PID controller in several key areas, including improved trajectory tracking performance, greater robustness against noise, and better maintenance of system stability under varying conditions. These findings confirm the effectiveness of the purposed Tube Model Predictive Controller for pneumatic muscle actuators. The Tube MPC's advanced performance highlights its suitability for controlling complex biomechatronic systems with nonlinear dynamics and parametric uncertainties. Thank you for your attention. I look forward for any questions you may have.